Okay, we're going to start recording this. All right, session is now being recorded. How about that? Let me go back here for a second. That's not what I want. That's what I want. First thing I always do is just review the schedule and where we're at and anything that's due. I believe tonight by midnight, your Module 1 notes are due. I think everybody got in the, at least in this class, got in the 6A questions. I have to check the other class. You guys are doing well. So, stay on top of your work. I appreciate that. Midnight, the Module 1 notes are due, and I think we pretty much went through all the Module 1 notes, and today we're going to start Module 2. So if you have your Module 2 notes, which you should have. I don't. Okay, check in any extras I put in the back. Okay. Yeah, just flip through there and see what we got. There we go, right here. Okay. Yep, Module 2 notes are in the back. Hopefully there's another extra. I usually only make one or two. There you go, you got it. All right, so right here, again, Module 2 notes, or Module 1 notes are due tonight. We'll start Module 2. Thursday we'll have a quiz, but it will all be on Module 1. Okay, so just make sure you've got your notes studied up. The next Monday we're off, but we have 2 days off, the 4th and the 5th. And then we'll start Module 3, water cycle. I don't, we may end up finishing Module 2 on the 6th and then go into water cycle. We'll see. We'll see how far we get today. I don't think we'll get all that far. We may get to heat energy, but we'll see. The main thing today, all right, we're there. Let me hop off of here. Let's take a look at, we'll take a look at that video. Where'd it go? Right there. So starting to understand how the Earth balances its heat, you need to understand a couple of concepts. Number one, heat transfer, specific heat or conductivity, and then the difference between temperature and heat. And so we're going to look at all three of those ideas first. Got a couple of videos on we'll watch. And then once we understand those three concepts, then we'll apply that to how the Earth basically regulates its temperature. And that's what the heat balance of the Earth is all about. Because it does it because of conductivity, heat transfer, three ways of transferring heat energy, conduction, radiation, all of that. And all of that comes into play to keep the Earth at a nice 59 degrees average all over the Earth and around. Pretty nice. So let's take a look at the first concept, which is the difference between heat and temperature. A little video there. Let's go ahead and share that. There we go. Who are my guys taking physics? Have I got anybody in here taking physics? No? Okay. They're all in my navigation class. But you'll see this, and you'll see some of the other heat transfer, specific heat, and all that stuff. You'll see those in your physics class, as well as if you've taken chemistry, you've probably seen this before as well. Hopefully this is a review, so let's take a look at it.
Hey you guys, this is Mr. Millings, and in this video we are going to learn about the differences between temperature and heat. So what is temperature? Well, it says right here that temperature is a measure of the average kinetic energy in the particles of a substance. So in other words, temperature is a measure of how fast the particles in a substance are moving. And at higher temperatures, the particles in an object have more kinetic energy and are going to be moving faster. And at lower temperatures, those particles are going to slow down and have less kinetic energy. So if we take a look at this graphic right here, we can see that there's some particles in motion. And let's just suppose that these are gas particles. And so what's going to happen to these gas particles as we increase the temperature of the gas? Well, as we increase the temperature of the gas, these gas particles are going to start to move faster and faster and faster, and therefore they're going to have more kinetic energy. So once again, temperature is just a measure of the average kinetic energy of the particles that are in that substance. And if we were to cool this gas down to a lower temperature, then these gas particles are going to start to slow down and they're going to have less kinetic energy. All right, so understand that relationship between temperature and the amount of kinetic energy that those particles have. They're directly proportional, right? As the temperature increases, so does their kinetic energy, and as the temperature of the particles decreases, their kinetic energy also decreases. And so now let's take a look at a simulation where we can apply this concept. And so let's take a look at this simulation, compliments of the University of Colorado, PhET simulations. Visit their website. They have a lot of really cool science simulations that you can take a look at. But let's take a look at this simulation right here. In this little container, we have some neon particles. And what we're going to do with this is we're going to take a look at what happens to these neon particles as the temperature starts to increase and decrease. And so right now the temperature of the gas that's in this container is 105 K. And as we begin to cool this gas down, what do you notice about the neon particles here? Well, if we take a look, we'll notice that they start to slow down. So as we cool something down, that is to say, as the temperature decreases, the kinetic energy of these particles also decreases. And if we cool this down more and more and more, these neon particles have less amounts of kinetic energy. If you remember, kinetic energy is equal to 1/2 the mass times the velocity squared. So if we slow down these particles, they're going to have less and less and less kinetic energy. And if we get this down to absolute zero, or 0K, which is the coldest possible temperature in the known universe, then what do you think is going to happen to these particles? What do you think is going to happen to their kinetic energy? Well, if we take a look, if we keep cooling this down and removing thermal energy from the system here, they stop, right? At absolute zero, particle motion stops. All particles have zero kinetic energy at 0K. All right, so understand that concept. And so as we apply heat, what do you think is going to happen to these particles? Well, you guessed it, their kinetic energy is going to start to increase. And so as we increase the temperature of these particles here, the kinetic energy of these particles increases. So all temperature really is, temperature is nothing more than a measure of the average kinetic energy of the particles that are in that substance. And if we continue to heat this up, approaching 100K, we'll notice that the average kinetic energy of these particles is increasing as their velocity is increasing, right? And so these little particles are hitting each other with more and more force as their velocity is increasing. We're approaching 150K right now, so these are getting pretty hot, and you'll notice that the kinetic energy is also increasing. All right, so understand that concept once again, that temperature is nothing more than a measure of the average kinetic energy of the particles that are in that substance, right? At higher temperatures, those particles are going to move faster and faster and faster and have more kinetic energy, and at lower temperatures, those particles are going to slow down and have significantly less amounts of kinetic energy. And so what is heat? Well, heat is a little bit different than temperature. Don't get the two confused. A lot of people confuse temperature and heat. They think they're the same thing, but they're not. It says right here that heat is a measure of the flow of energy due to temperature differences between objects, all right? And that heat always flows from hot to cold, and we can measure heat in something called joules. All right, so let's suppose we have some sort of styrofoam container right here, and in this
Okay, I'll pause right there. When we saw pressure gradients, right? In the last class, we talked about how wind moves, right? How a fluid moves from one place to another is because of a difference in pressure, right? Or pressure gradient, right? Y'all remember that? Temperature actually works kind of the same way, or heat and temperature. If you have a temperature gradient or a difference in temperature, right? Heat energy is going to move in joules. Okay, and I'll prove it right now. What I want you to do is the table here is probably, I don't know, 60 or so, 65, 60 degrees Fahrenheit. I don't know, figure conversion. Take away 32, so about 35, take about half of that. And it's about 16, 17 degrees Celsius. Okay. Your body is right now 37 degrees Celsius, or about 98. Okay. So there's a temperature difference of probably about 25 degrees between them. Okay. There's a temperature gradient. So, right now. So what I want you to do is put your hand on your desk. Okay. Feels cool, doesn't it? Okay. That's because you've got probably about a 25 degree temperature. Where's the heat energy go? Into the table from your hand. Okay? That's not there, put your hand on. Okay. So, there's a point. Okay, so it's feeling cold and cold and cold, right? All right. So go ahead and pick it up and put it on your sheet. Nice and cold, right? You lost a bunch of heat energy out of your hand that went into the table because they tried to equalize in that spot. In fact, if you feel the seat where you're sitting, you've already transferred a bunch of heat out of your body into that seat, right? So the pressure gradient, if you will, was about 25 degrees, and the heat moved from your warm hand, right, into the colder desk. So that's what he's talking about here. To measure the flow of energy, you have a flow of energy from your hand into the desk. Due to the temperature differences, which again was about 25 degrees or so, and then the heat always flows. When you don't know, go hot to cold, okay? Always hot to cold. And of course, that heat energy is, any energy is measured in joules in the metric system. Okay, everybody see the idea here and the difference between temperature, which is the mover, it's like pressure is in a fluid, whereas the heat energy is like the wind movement from one place to another. Okay, hope that one worked.
Styrofoam container, we have equal masses of water right on the left hand side as we do on the right hand side. And so this styrofoam container is separated by a thin little piece of metal, and we know that metal conducts heat. And so right here on the left hand side of this container, we have water that is at 90 degrees Celsius, right? So it's pretty hot, right? It's on the verge of boiling. And on the right hand side of this container here, we have water that is pretty cold. It's at 10 degrees Celsius, right? It's on the verge of freezing. And so what's going to happen if you have this styrofoam container that is separated by this thin piece of metal and set it somewhere for a couple hours? Well, what's going to end up happening is this. If we take a look right here after a couple of hours, what will end up happening is that the hot water is going to transfer some of its thermal energy, right? Some of its heat is going to get transferred to the cold water, right? Heat is always transferred from
It's like your hand
hot
into the
to cold.
desk.
Keep that in mind, never the reverse. So when we come back in a couple hours, what will end up happening is that the temperature of this water here will end up being 50 degrees Celsius, and the temperature of this water right here will end up being 50 degrees Celsius, provided that we have the same amount of water in this on this side of our container as we do on this side. So let's suppose we have 1.5 liters here and 1.5 liters here. We have equal amounts of water, and therefore the temperatures of these of the water is going to level out over time. So how did we figure this out? Well, to get the final temperature, what we ended up doing is we ended up taking the temperature of the water on the left-hand side, which was 90 degrees Celsius, plus the temperature of the water on the right-hand side, which is 10 degrees Celsius, and we ended up just dividing this by 2. And so what we end up
It's like an average to me.
what we end up with right here is 50 degrees Celsius. So when we come back in a couple of hours, this container is going to have water that is 50 degrees on the left-hand side and 50 degrees on the right-hand side, and they're going to level off. All right, so that is what heat is. Heat is a measure of the flow of energy due to temperature differences, right? And so this right here is a temperature, a measurement of temperature, right? This is a temperature. They're going to level off at 50 degrees Celsius, but we can actually measure how much thermal energy or heat this side absorbed and this side loses. And we can do that in a unit of measurement called the joule, Joule, or capital J for short. Okay, so understand that concept where temperature is a measure of the average amount of kinetic energy of the particles in that substance, and heat is a measure of the flow of energy due to temperature differences. So let's take a look at a little simulation now that hopefully summarizes what we're talking about right here. And so in this little FET simulation from the University of Colorado, we can start to see heat transfers that take place between different objects. And so if we take a look right here, we're going to go ahead and put this water on this little heat source right here. And what we're going to do is we're going to heat this up. So we're going to heat this up, get it to be pretty hot, a pretty warm temperature, let it do its thing. And so once this heats up, we're going to go ahead and drop in a thermometer just so we can see the temperature of this. So we're heating this water up. It's getting pretty warm. And so what we're going to do now is we're going to place a thermometer right in here, and we can see that the temperature of this water is pretty hot, right? Those water molecules are moving with a lot of kinetic energy. They're moving faster and faster as we heat this up. And so what we're going to do now is we're going to put this brick on this little heat source right here, and we're going to remove thermal energy from this brick. We're going to cool it down, right? So we're going to cool this down. And so if we get our thermometer and put it next to this brick right here, we can see that our thermometer is going to cool down, right? So we're cooling this thermometer down. I'm sorry, we're cooling this little this brick down. And so we're going to heat this water up. And so what do you think is going to happen if I put this really cold brick in this really hot water? Well, let's find out. Let's take a look at what happens. Let's take a look at the heat transfer that takes place. So we're going to take this brick now, we're going to put it into this hot, scalding water, and we're going to take a look at what happens. And as you see, if you take a look at this thermometer, what ended up happening is that the temperature of the water is dropping, it's decreasing, right? The temperature of the water is decreasing, but the temperature of the brick has increased over time. And what ends up happening is that these two temperatures here are ultimately going to end up being exactly the same over time. They're both going to level off and be about the same temperature if we remove the heat source from both of these items. Okay, so heat, once again, is a flow of energy due to temperature differences, and heat always flows from areas of warm or hot to areas of cold. So when we put this cold brick into this little this pot of boiling water, the warm water transferred its thermal energy or heat to the cold brick, and so you had a leveling off of the temperatures there. And so let's take a look at what happens when we use the iron. So we're going to go ahead and put this on our little heat source. We're going to speed this up here. We're going to heat this water up to a really hot temperature. We're going to get this water boiling. And so now we're going to put our thermometer in this pot of water here, and we can see that it's very hot, right? It has a lot of kinetic energy. Let's heat this up a little more. And so now what we're going to do is we're going to take this brick here, we're going to put it on this heat source right here, and what we're going to do is we're going to remove the heat. We're going to remove thermal energy from this iron block right here. We're going to warm this water up some more. And so let's take a look at what happens to the temperature of this iron block when we put it in this water. When we put it in this water, we can see now that the temperature of the water and the temperature of the iron are going to even out, right? The temperature of the water is decreasing as it transfers some of its heat to the iron
There's
block,
a
right?
formula you
So
can
the
actually
block
figure
was
out
pretty cold before, and those iron particles have
exactly
low
how much
amounts of
heat
kinetic
transfer.
energy. They're absorbing thermal energy or heat from the water, and so the temperature of this iron block is increasing while the temperature of the water is decreasing. And over time, those are going to level off and be about the same. So once again, this little simulation just kind of shows you what heat is. It's a transfer of thermal energy. It's the flow of thermal energy due to temperature differences between the two substances. And so if you like what you see, go ahead and click that little bomb in the bottom right-hand corner. And
Okay, we'll stop there, and let me share the notes. Let's preview the notes real quick. It should be right there. No, it isn't. It's right there. DocX. Okay, really quickly. Let's make it just a little bit bigger. There we go. All right, so just to begin with, and what you should start looking at on your notes here is, of course, you need to understand what matter and energy are. We just talked about thermal energy and heat energy, and we talked about how it's transferred, and I gave you a little demonstration on your hand on how heat is transferred. We'll define temperature, which was in the video, and we'll talk about three primary temperature scales, and we'll be able to convert between the three. And then we'll talk about the basis for references in the Celsius and Fahrenheit temperature scales. So we'll get, let's see, this is a video we just watched, is temperature and heat. So what I want to do, let's take a look at, and let's look at the PowerPoint before we look at, I've got another video, but we'll go over here. Let's take a look at the beginning of the PowerPoint. Okay, should be right there. Okay. All right, let's take a look at the video if I got it. Yep. All right. So, very quickly. Again, we're going to look at temperature, density, heat exchange, and heat balance right here. The references for this particular section is chapters 5 and 7 in your textbook. Did anybody not get a textbook that wanted one? Because there's one more in the back. That was you. Okay. I knew I made 5. We need a 1 or 1.5 inch 3-ring binder. There you go. Okay. So if you look at three chapters, chapters 5 and 7, and that covers your temperature and heat exchange, heat balance. Okay. Again, what are we going to cover? We're going to do a basic determining how temperature changes and the heat energy in the atmosphere, and the resulting temperatures that in the gases of the mixture. We'll talk about that. We know that air is matter. Why? Because the definition of matter, oops, this is in your notes, is anything that has volume or mass, and mass. Okay? If it has mass and takes up a volume, then it is matter. And then energy is the ability to do work, and can come in different form. All right? So that's your two definitions you need right away. So since atmosphere is a gas, and it's actually a mixture of gases, okay, it has volume. Now that volume is not definite, it can be compressed because it's gas, but it definitely has mass. Thermal energy, again, comes from, we just saw this, the internal motion of the matter, okay? And then heat is the amount of motion or kinetic energy that moves from place to another, okay? So heat can be transferred by 3 ways: conduction, convection, and radiation. We'll talk about all 3 of them. Temperature, again, is a measure scale on the amount of heat, and it's usually by a thermometer or any other temperature sensing device. And it always travels from high temperatures to low temperatures. So, that temperature is to heat transfer as pressure is to fluid movement. Okay, they kind of work the same way. Of course, there are 3 different temperature scales, and we'll look at all 3 of them. For weather-based thermometers, okay, have a cotton region shelter like this. It's basically sheltered. It'll have a maximum thermometers. Normally, the max will be a mercury thermometer. They're getting away, obviously, of mercury thermometers because it's poison. Those thermometers, especially cool the alcohol thermometer. Anyway, we also know that if you wrap 2 wires together and change the temperature of those on the wire, it'll actually create electrical flow. Okay, and that's called a thermistor. Okay. Temperature scales. All right, 3 different scales: Celsius scale, Kelvin scale, and Fahrenheit. We saw in that demonstration, the neon, they were using K, which is the Kelvin scale, which is, right, where is it here? I said negative 273 Celsius. So Celsius scale, I'll put it up on the board here. Let's start with that. All right. What they did is they took a standard pressure. Y'all remember that? 14.7 psi, or 13.2 millibars. And they had a standard temperature, 15 C, or 59 degrees Fahrenheit. They had a liquid, water, at those parameters, and what did they do? They froze it. And they said, all right, where this thing freezes, we're going to call that 0. That was easy. And then where this thing turns into a gas, we're going to call that 100. And since it's a metric system, it's based on, the 10 digits, right? Metric system is always based on base 10. So they just divided it up. Boom, boom, boom. 9, 10. There you go. And that's how they came up with the metric system. Super simple. It is. Yeah.
And American science is less heat.
Yeah, we
because everybody has the same type of heat, so it makes sense. Heat better.
Yeah, use your feet, right? Yeah. But yeah, feet in centimeters, like that, or meters. Okay. Now, what later on, as they were doing demonstration with a gas, what they did was took the temperature down and measured the pressure as it came down. Okay, and pressure is a result of the movement of the molecules. And so all they did was say, all right, at this temperature, well, let's do this. At this temperature, the pressure is there. 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 And man, theoretically, they just ran the line down there. Theoretically, right? When the pressure is 0, there's no kinetic movement, theoretically. And so if they extended the temperature scale, boom, boom, right? And the pressure scale all the way down to 0, 0, it came down to minus 270 degrees Celsius. So we call that 0K. And you don't have to use the little degree sign when you're using Kelvin. Okay? Well, if that's the case, what's the temperature of the freezing point of water at a standard atmospheric pressure in Kelvin? Just look at the scale. Well, 0 is minus 273. What's freezing point in Kelvin? Who's buried in Grant's tomb? Grant, right? Kind of obvious question. What would you add to this to get 0? 273. Thank you. That was hard. All right. So 0 Celsius is 273K. That's how you would convert from Celsius to K. It's just you add 273. How about the boiling point? Add another 100, right? Right? Okay. You got by that?
I'm on it.
All right. 373K is 100 degrees Celsius. Okay. And so again the Kelvin scale is 100% based on absolute zero and the Celsius scale. Super simple. Okay. So just to convert from one to another, you just add 273. Of course, if you're going from here to here, you just take away 273. Okay. All right. Fahrenheit, yeah, Fahrenheit. It's the same scale, but now the freezing point's 32 degrees Fahrenheit, and the boiling point is 215. Well, add 100 plus 180 to this. That's 212. Okay. 212 degrees Fahrenheit. Oh, what did we notice? There's 180 there, and there's 100 here. So if I'm going to convert from Fahrenheit to Celsius, I've got to take that 180 degrees over 100 degrees into account, don't I? Okay. Anybody seen the conversion factors? Like, all right. Why don't I just, if I'm at 10 degrees Celsius, why don't I just, I don't know, I'm going to go 9/5 C, and then I'm going to add 32. That takes care of the 180, right? If I 180 over 100 is 9/5. See how I did that? And then I got to slide it up the scale to take care of the 32. Okay? Hey, real simple. Double it and add 32. Isn't that close to double? That's what I used to do when I was over in Europe and stuff. All right, I want Fahrenheit. All right, let's see. This is 10C. I just double it and add 32. About 52 degrees. That gets you in the ballpark, doesn't it?
Yep.
Okay. Double it and add 32. I like to keep it easy. If you really want to do it right, though, it's 1.8, right? C plus 32. All right. Well, now I'm at, say, 95 degrees Fahrenheit, and I got to go to Celsius. You do it backwards. You got to take care of the 32 first. All right. So I'm going to take away the 32. It's going to give me 63. And then I'm going to take half of that. Right? Which is going to be about 31.5, give or take a little bit. That's about 31 degrees Celsius. Actually, if I really want to be accurate, it's the 5/9, or I would divide it by 1.8 to get it right on. Okay? So, if you're confused and you want Fahrenheit from Celsius, double it and add 32. You want to go the other way, take away 32 and take half. That makes it really simple, doesn't it? Yeah, chemistry class, they all got that screwed up.
I just know because I grew up.
Yeah.
More into the world.
Yeah, you grew up with every place except the United States uses the Celsius scale. So yeah, it's, of course, as soon as you go, you drive across the border to Canada, you're in your kilometers. Driving to Mexico, the speed limit's in kilometers. Oh, the speed limit's 180. I'm going to go 180. Okay, kilometers per hour or whatever. Okay, so you got to figure, you got to figure it out. So the conversion factor again from Celsius to Fahrenheit, it's 9/5 times your plus 32. Okay, from Fahrenheit, 5/9 minus, oh, excuse me, my bad. Fahrenheit minus 32, there you go. And then take half. Okay, Fahrenheit minus 32, and then take half. You got to take care of the 32 first. Okay? But explaining it that way, does that kind of make sense? Okay. Double and add 32. Take away 32 and then take half. So if you're not sure, do that first and then do the real math, right? Okay? Everybody cool with that? Cool. All right. Everybody cool with Celsius to Kelvin, Kelvin to Celsius? You might see one later on the test.
So when do you see Kevin?
Say again?
When do you see Kevin?
One more time.
What do we see it as?
Kevin? Who uses Kevin?
Yeah, only if you're really working with a scientist. Yeah.
Not on their record.
Yeah. Or if you're in a chemistry class. Yeah. Or if you're in a, yeah, okay, yeah, you guys keep going. It's really useful because mathematically, people don't like to use negative numbers. That's why. So, and when you're talking about, say, the temperature of liquid hydrogen, or the temperature of liquid oxygen, or liquid neon there, okay, that was really cold. So, yeah, if you're dealing with things at very low temperature, for us, Celsius works fine. You know, we're in the 0 to the 100. In fact, if you get above 50 Celsius, all right, what's 50 Celsius in Fahrenheit? Double it. It's 100 already. Add 32. Yeah, you're talking Death Valley right there. Okay. I've been in 47 in Yuma, Arizona. Let me tell you. Yeah. Okay? Look okay? We're cool with that. All right. So those are our three temperature scales. Let's see if that's the next one I wanted to do. Oh, yeah, conversions. Didn't I just go over that? All right. So Kelvin to Celsius, just add 273. Celsius to Kelvin, just take away. Fahrenheit to Celsius, take care of your 32 first, then divide it by half or 1.8 if you're really being accurate. Double it, and then add 32 for your Fahrenheit. Okay? And of course, to get you in the ballpark, keep it simple. All right? All right, transfer of heat energy, we will stop right there, and we'll come back to it. Notes, where are we at? Let's talk about heat transfer and heat capacity, because both of them are very important when we talk about the Earth's energy balance.
Temperature object. In this video, we will discuss the three main types of heat transfer: conduction, convection, and radiation.
Conduction is the process by which heat energy is transferred through collisions between neighboring molecules. To further explain this concept, let's examine a frying pan on a gas stove. As the flame heats the metal, the molecules that have direct contact with the flame start to vibrate. These molecules then vibrate against neighboring molecules, which in turn vibrate against their neighboring molecules until all the atoms that make up the pan are vibrating. This movement or vibration of the molecules releases heat. At this point in conduction, if you were to touch any part of the pan, you would burn yourself. How well an object conducts heat depends on the bonding within the atomic and molecular structure. Solids are usually the best conductors of heat because their particles are tightly packed, as shown in the figure at the left. Liquids and gases can conduct heat, but in order for conduction to take place effectively, they have to be contained. The reason for this is the particles of a liquid are close together but have no definite shape. Gases also have to be contained for conduction to take place because they have no definite shape and their particles are spread apart, as you can see in the figure to the right. Poor conductors of heat are called insulators. An insulator is designed to reduce the rate of heat penetration. In other words, insulators slow down heat transfer. Some of the most common insulators are wood, rubber, cotton, plastic, and glass.
Convection is the process of heat transfer caused by the movement of fluids. The movement in the fluid carries energy as it flows. It is this movement of liquids that allows for energy to flow through the whole substance. As a fluid is heated, molecules move faster, spread apart, become less dense, and are buoyed upward. Then the fluid that is cooler and more dense sinks towards the bottom where the process is repeated. This process is what we call convection. It is very important to note that convection is a type of heat transfer that can only occur with liquids and gases. Because convection is defined as heat transfer due to the movement of fluids, it is not possible to occur within solid structures. Something that we see on a daily basis that is an example of convection is boiling a pot of water. When we heat up a pot of water, the water at the bottom is quickly heated. As it heats, it becomes less dense and pushes upwards. When this occurs, currents within the fluid appear. The hot water rises, pushing the more dense, cooler water towards the bottom of the pan. Then the process begins again to warm up the cooler water that is now at the bottom. These currents continue to move energy as the water continually heats up and eventually begins to boil completely. We can also see convection in our atmosphere and is part of the weather that is around us. Convection currents in the atmosphere actually make it possible for us to feel wind. Like we can see in this picture, as air is heated by the sun, it rises because it is less dense. As it rises, it pushes the cooler air towards the surface of the earth, where it heats and then rises again. Convection really is all around us, even if we don't realize it. Now that we have a basic idea of what convection is and where we see it, we can now learn that there are two types of convection: natural convection and forced convection. Both of these forms rely on the movement of fluids that carry energy to produce heat. However, as their names imply, one is natural and one is forced. Natural convection has a driving force that occurs due to natural differences in density. Forced convection moves fluids by use of fans, pumps, or other devices. Natural convection can be seen in the example we talked about before of a pot of boiling water. The movement of water occurs naturally when heated because the density naturally changes. As for forced convection, we can think of an enhanced fireplace. Some fireplaces have fans installed to help propel more heat into the room you are trying to warm up. Another common method of forced convection is a convection oven. These ovens also have a fan that helps rotate the air inside the oven.
Radiation is the transfer of heat that occurs through electromagnetic waves. Radiation is everywhere. Although we most often think of the sun radiating heat, most everything around us radiates energy. The grass, your car, even we do. There are two factors that determine how much heat something radiates. These are temperature and surface area. The sun has many types of waves that it emits. The ones we can see are between 400 and 750 nanometers. The majority of the waves that the sun emits are ultraviolet and infrared, but it also emits microwaves and radio waves. The Earth radiates much less heat, and most of its radiant waves are infrared. Everything has either a high albedo or a low albedo. Albedo is how reflective something is. Objects of light colors have a high albedo. They reflect heat very well, while objects of darker colors have low albedo. They absorb heat very well. The Sahara Desert has a very high albedo. Its light sand reflects heat, making it hot during the day, but because there are no white clouds reflecting the heat back in, the heat escapes easily, and it can get very cold at night. The rainforest, on the other hand, has a low albedo and absorbs heat very well. That is why it is so warm and tropical. You may have heard people talk about the greenhouse effect. This is when the radiant energy comes into the atmosphere of the Earth but cannot escape because of the clouds surrounding it. White fluffy clouds reflect heat back to the Earth, while dark storm clouds absorb the heat.
We hope you enjoyed this video and learned more about conduction, convection, and radiation.
Okay, when we talk about conduction, convection, radiation, on the Earth, mainly, can there be any conduction and radiation in the vacuum? Or conduction, radiation, or convection in the vacuum of space? There's only one kind of energy really that can go from one place to another. And so we get our energy from the sun in the form of electromagnetic energy, which is your radiation. Mostly infrared, okay, or visible light, or UV, A and B. These and X-rays too, but the ones that actually create the heat on the Earth are those frequencies of electromagnetic radiation. Okay, and she said everybody gives off some sort of radiation, right? Let's prove it. And what you do is put your hand right above your arm like this. Don't touch it. Right above it. Feel the warmth coming off it? Good. That's mine. All right. All right. You're not touching it, are you? Okay. So that is infrared radiated heat in the forms of electromagnetic energy. If if you fly around with an IR sensor, everybody gives off heat. Okay, that's how the cops find people. They'll look at and stuff, and they'll see glow from an IR sensor of somebody's body or okay. So infrared definitely. Now once we get down to the Earth though, the two main conductors of heat is conduction and convection. Okay? Think about the oceans, which out here, well, if you looked on the Weather Channel lately, what's the temperature of the waters in the Gulf of Mexico right now? You ever been watching the hurricane that's coming on the west coast of Florida? Won't beat us later, so they say. What's the temperature of the waters in the Gulf? Anybody look? About 90 degrees. Yeah. Okay. That's what spins up the hurricane. Right? Okay. But isn't the air in contact above that to the ocean waters? And does that 90-degree ocean water conduct the energy into the lower parts of the air? Sure, they're in contact. But once they're in contact and that air warms up, where does it go? Up. Okay, now you're dealing with the motion or movement of energy that's being moved in the gas. Okay, the same thing in the water. It gets moved around in the water as well. One huge convection current called the Gulf Stream. Okay, that's one huge convection current. We already looked at convection currents with land breeze and sea breeze. Okay, so those are in fact convection currents, and we move around the energy on the Earth by radiation a little bit, because the Earth also sucks up a bunch of energy and then radiates it back out into the atmosphere. Okay, so it sucks up infrared, visible light, UVA, UVB, and some X-rays, and it warms it up. All right, but weren't you just radiating heat back out into the atmosphere? Well, the Earth does too, in the exact same way. With my earth science classes, I used to take a tennis ball and warm it up, right? And then it would radiate its heat back out into the atmosphere. Earth does it exactly the same way. And that's IR radiation. But also, is that warmth, both the water and the land, is that in contact with the atmosphere as well? So it will either heat up or cool off the atmosphere by conduction. Conduction, radiation, all happening. And they play a really important role when you talk about the Earth's energy balance, which is what we're going to talk about. But it's kind of crazy, because some things will heat up and some things won't. Some things can store a lot of energy and some things can't. We'll take a look at that real quick. Maybe we will. Okay. All right. Let's talk about heat capacity real quick.
Different amounts. Different fluids, I guess I could argue as a 21st century scientist, different fluids store heat differently. So we need to find a way to account for that. Once I finish writing this, we need to find a way to account for this fact and maybe study it in a little more detail. But the one thing that's pretty obvious is that if you put a pot of, I don't know, gold on the stove, and you put a pot of water on the stove, and you put a pot of molten aluminum on the stove, and they're on the stove for the same amount of time, they won't be the same temperature. So different things are able to either better or more poorly store some amount of heat. And we can describe this by a quantity called heat capacity. This is a very, very easily misunderstood quantity. So let's talk about it for a little bit. Heat capacity, I'm going to define as capital C, and it is Q, that's the amount of heat going into the thing, divided by the change in temperature. So something that's able to store heat very efficiently, you give it some amount of heat and the temperature doesn't change very much. Water is one of these awesome substances that stores heat very efficiently. And something that stores heat very poorly would change its temperature a lot for a given amount of heat. So that would have a very, if it changes its temperature a lot for a given amount of heat coming in, then that would have a very small heat capacity. Something has a heat capacity if it's able to efficiently store energy. Like a lot of heat pockets, you could say. You get this kid and he's putting on some of these cargo pants, and you know, he's wearing these cargo pants, and they're they've got a pocket here and 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 4 pockets on the back. Can't even show them, but all those pockets enable that kid to store energy very efficiently. That's analogy is breaking down, so we should stop that right now. But I want to define this Q a little bit gently. Here's what I want to say. Q is positive if heat is adding to the system. And this, you're going to find a lot of people who disagree with me. This is a definition that I'm making right now, and I like it. I think it makes more sense than what the chemists say. Q is positive if heat is added to the system. Many people use the exact opposite, and it's really frustrating going between the two sets of equations, but I'm going to stick with my side, and that's what it says. And Q is negative if heat leaves system. Of course, this requires the definition of some system in which you're interested, but we'll always define something we're looking at and the rest of the universe as the other. So that will be fine. So heat capacity is cool, but think about it like this. If James Joule had a tiny little paddle device and he added a certain amount of energy to a tiny little bowl of water, it would heat up a lot. But if he had that same amount of energy and he added it to a big pot of water, then it would not heat up very much. And we certainly don't want to describe water by its heat capacity because it depends on how much water you're talking about. So we're going to talk about something more specific. Oh, let's call it specific heat. And rather than just this definition, I'll define something called specific heat. Let's use brown for that. Specific heat.
Now you're adding mass.
Specific heat just takes that same heat capacity and divides it by mass. So specific heat is a lowercase c because look, it's so much smaller. See that? This is really big. And that's much smaller because we're dividing per unit mass. How much can each unit of mass store? And so that's just going to be capital Q divided by M times delta T. Those of you who may be studying for an exam in medicine would be edified perhaps to see that Q then is equal to MCAT. See? So you can remember that. What fun. That is the heat that goes into a substance. Well, I guess it depends on the mass, right? And it depends on the specific heat. Oh, yes, it quite does. And it depends on the change in temperature of the system. This is not the right way to look at this, though. I want you to look at it like this. The change in temperature of a substance depends on the heat that goes into it. Yeah, more heat change is going to change the temperature more. But also, it depends inversely on how much mass you've got. You got more mass, it's not going to change the temperature as much, of course. And it depends inversely on the specific heat. So if the specific heat is big, the change in temperature will be small. And if the specific heat is small, it's not a very good material for storing thermal energy, then you'd find the change in temperature to be big. Awesome. And you can do cool things like calorimetry. And this is an enormous activity, and I'd certainly encourage you to consider it. I'm going to say that if I have some liquid in this beaker, let's make it a gray liquid. What if I had mercury or something?
We already saw this in the
So if I
simulation.
have some liquid in here and I drop in some metal block, this is, let's say this is the mass of my block, and this is the mass of my liquid, then we can figure out what temperature those guys together would come to. So I guess maybe the block is hot and the liquid's cold, or maybe the liquid's hot and the block is cold. It doesn't really matter. But if we wait for an infinite amount of time, yeah, this is going to be a long lab. If we wait for an infinite amount of time, then we'll find that they reach ultimately the same temperature. So I can write that as the heat for the block plus the heat for the liquid is equal to 0. So one of these suckers is going to be losing heat. Let's say the block's losing heat. Then Q for the block is negative, and Q for the liquid is positive. And if you add those two together, you get 0. I'm assuming that we insulate this sucker, because if it's not insulated, this will not be true. You got to be careful. All kinds of ways for heat to leave a situation. So insulate it very carefully. But I know that the heat that left the block, check this out. This is our equation for heat. Remember MCAT? The heat that left the block is the mass of the block times the specific heat of the block times the change in temperature of the block, which is the temperature final. They'll come to the same temperature. So it's not going to be the temperature of the block final. It's going to be the temperature final. Okay. And then I'm going to subtract the temperature of the block initially. And then I have to add on the mass of the liquid times the specific heat of the liquid times that change in temperature of the liquid, which is the final temperature of the liquid, same as the final temperature of the block, minus the initial temperature of the liquid right there. And this stuff is all equal to 0. So with a flurry of algebra, you can find the final temperature of the mixture. You can also find anything else in here that you want to find, but I'll just point out that that would be the mass of the block times the specific heat of the block times the initial temperature of the block plus the mass of the liquid times the specific heat of the liquid times the initial temperature of the liquid, divided all by the mass of the block times the specific heat of the block plus the mass of the liquid times the specific heat of the liquid. Look at this. It's a weighted average. Of course it is. You've got temperature in both of these terms. You don't have temperature in both of those terms. This is a lot like average location of a mass, or what did we call it? We called it center of mass. This is the position of the center of temperature. Oh, and so the thing that's got more mass or a higher heat capacity is going to have a greater significance in the final temperature. If I have a big block, then it will greatly change the temperature of the liquid. If I have a small block, it won't change the temperature of the liquid very much. I suppose all of this makes fantastic sense. Next, we'll talk about heat flow. Bye-bye.
Okay. Now, where did they come up with that C? Okay, where in the world do they come up with that C? By experimentation. And in fact, let's see, let me go back here. If you go down a little bit, there is a common, if you want to click on the, just above module 3 there, common specific heats. Go engineering toolbox, all right. All right, let's take a look at that. they're calculated, okay? And the units for that is joules per kilogram Celsius. And that's how much energy over what the mass is and the temperature change, okay? So let's take a look at some common, let's see. Check out, first off, quartz. Go down and see quartz. A lot of your sand, isn't that quartz? If we're at the beach, let's see if it's on there. Quartz, quartz, quartz. There it is. 730 is the specific heat. Okay, and that's kind of medium. How about copper? Okay, let's go back up here. Where's copper? Copper, copper. There it is. All right, 385. What's that mean to us? That means it will suck up 385 joules for 1 kilogram of copper, and the temperature will go up 1 degree. Y'all cool with that? All right. How about water? This is where we were talking about the sea breeze. Go on down and flip on water there. Holy crap. It takes 4,182 joules of energy to raise 1 kilogram of water, which by the way is 1 liter, 1 degree. That's what well over 10 times that of quartz or copper or most land. Isn't this why we have a sea breeze? Because the ocean and the land get the exact same amount of energy from the sun, don't they, on any given day? But that land heats up a lot faster than the water does, because it takes 4,100 and some change of joules to raise 1 kilogram of water. Also depends on the mass too. There's, ocean water is probably, the mass is a lot bigger than the land. But this is why the temperature goes up and down in the land so much faster than it does in the water. It's because of that specific heat. That's kind of where I wanted to wrap it up. Did that make sense? Mm-hmm. Okay. So that's where specific heat comes in. Is how fast and how slow will the temperature rise and fall? Okay. And oh yeah, by the way, isn't that going to make air move around or not move around? Okay, so we'll talk about that a bunch. Okay. Back to the PowerPoint, let's see, real quick. I got about 10 minutes, so we'll use them all. All right, so we already talked about on the Earth, the heat will transfer around by conduction, convection, radiation. All 3 modes of heat transfer you'll see. Okay, and again, radiation is simply electromagnetic energy. And on the Earth, generally, we're talking about infrared. If you stand in front of, a cold day, most of the time, you put your hands out in front of the fire, you're trying to warm up, and you feel the heat coming off it, that's infrared radiation. Okay? And of course, the Earth is, in fact, heated by infrared radiation and UV radiation, and visible light has energy as well. So all 3 of those transmit energy into the Earth. Okay? Conduction, of course, is you did conduction on the desk, didn't you? Okay? Is by touching. Right? Transfer of energy from substance within any substance when it is touching, basically. Very effective in heating metals. But air actually is a very poor conductor. Okay, did you know that air is a crappy conductor of unless it moves? So during the winter time, what do? You put on a sweater, right? Then you put on a jacket. Your heat from your body warms up the air inside the jacket, and as long as it doesn't move, it's a good insulator.
course, now you're out, you're running around, you got your jacket on, you got to cool off. What do? Open it up. And that warm air goes, out it goes. All right? So now by convection, you have cooled off. So now you got conduction and convection. But if the air is not moving, it's actually a fairly poor conductor. Okay? But if it is moving, it transfers energy very, very well. Okay? Of course, we need more water. That's another one. Air at the temperature acts like fluid because it is a fluid. And so as soon as you have a differential difference in density, you're going to get the energy that's in that fluid moving from one place to another. Really, really important when we talk about the Earth's energy balance. Okay? There's radiation. You can put your hand on top of conduction, touching something. Which one's which? What would you call this one? Which one's conduction? Which one's convection? Which one's radiation? I call this one what? Well, this one should be what?
Yeah.
Okay. Right. Conduction, convection, radiation, and the summary of those three. So again, how do we get our energy? Pretty much terrestrial, solar and terrestrial radiation. All right. Most of the radiation that warms the surface of the Earth, again, UV, visible light, infrared. UV gets sucked up in some UV gets sucked up in the stratosphere by the ozone layer, but these are called short-wave radiation because their wavelength. Infrared is actually called long wave because it has a longer wavelength than light and UV. So if I say, hey, we're getting, shortwave, the visible light and infrared, we're getting shortwave from the sun, but when it re-radiates out, when the Earth warms up and then it gives it back out into the atmosphere, okay, if there's a temperature difference between the atmosphere and the Earth, this energy is going to go back out. That's going to be your long wave radiation. Okay, your infrared is long wave, visible light, and our shorter wave. Okay, it gives like spectrum. See that right there. The highest energy radiation, such as X-rays and gamma rays, are diverted by the Earth's magnetic field, so we don't get most of those. Okay, they ended up at the North and South Pole. Right? Surface of the Earth, again, absorbs that short wave and some long wave electromagnetic radiation warms up. And then if the atmosphere is colder than the Earth, it's going to give its energy back out, isn't it? Okay, we know that energy travels from a high temperature to low temperature. Okay? But that's going to be just about 100% infrared radiation when it transfers. Okay, so it could be long wave radiation. But you see the difference between short and long wave. Short wave, and I'm going to ask you later anyway. Short wave is UV invisible light. Long wave is infrared. Why? Right here. You can see short wave, there's the short wavelengths up here. Longer wavelengths down here. So just right in here on the other side of the visible light spectrum is infrared. Up here, just on the other side, is your UV, ultraviolet, above violet. Okay, Roy G. Biv, everybody remember that? Yep. That's the visible light spectrum. Roy G. Biv, ever heard of that one? Okay. All right. The light that we see is Roy G. Biv. Okay. This is higher energy. And shorter wavelength. And L, the lambda. Up here is UV. Down here is IR. Okay. Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. So if you have a glass, if your glass at the house won't trace, the light into the visible light spectrum. Boom. Red, orange, yellow, green, blue, indigo, violet. This is lower energy, and longer wavelength. Okay. So if I was going to say, hey, which has more, oh, by the way, ultraviolet above violet, right? Infrared below red. Infra means below. How about that? Okay, there's your science lesson. I'm below red, infrared, above violet, ultraviolet. Okay, and they break UV into UVA, UV. Okay, so which one up here has more energy? UV or IR? Which one will burn you worse? UV, yeah, because it'll penetrate your skin. Generally, IR won't penetrate your skin, it'll hit the surface. Okay, but it'll burn you. You know, IR will burn you. But UV will penetrate your skin and burn you. That's why you get blisters if you get a real heavy sunburn. That UV has penetrated your skin. Okay, and visible light too has energy. It can burn you. All right. So, conductivity and heat capacity. All right, we already talked about heat capacity. How much energy can you put into a piece of something and have the temperature go up? We already saw that in the video. Okay. Conductivity is how well does something conduct heat. I'll tell you what, if I'm going to grab a pan, I'm going to, a hot pan on the stove, I'm going to have me, something that's going to insulate that, right? Grab me a mitt, or hopefully it may have a rubber handle. Those are things that do not conduct heat very well. Above, we found this heat capacity, right? The specific heat of the substances on food. You guys look at that. There's a table right above it that actually is a table of conductivity. How much will something conduct heat? Okay, which basically tells you the same thing. What I wanted you to take out of that is to compare water with some of the other elements. What conducts heat very well? Okay, and so there's a table of conductivity of specific materials. We're not going to look at it, but that heat capacity one. So, temperature response to adding energy into it will depend on the mass, and it will depend on the makeup of the material, and we saw that with the can something conduct heat? Copper, right? Aluminum and copper are your two main metals that they use for cooking, right? And maybe a good old cast iron pan, right? Those are fairly good conductors. Right? Water is not a good conductor at all. But I want to think about it. What's your body temperature? About 98. Okay, 37 Celsius. If you jump into water in California, which is cold, really cold. Let's say it's 70 degrees. Okay. What's the mass of ocean water? Huge, right? And now you have a 27-degree difference, right, between your body temperature and the water. Where does the heat go? Just like on the table, where did the heat go? How long are you going to last in that water? When your body temperature hits about 91, you go to sleep. When it hits about 87, 88, you go to sleep for good. And it's called hypothermia. Okay, you got to die. But, yeah, think about that, and when you talk about heat transfer, you got that huge mass of ocean water. You're jumping in it, and you're, that 25 or even 25 degrees difference. All that energy in your body can try to keep up. It's going to create energy and it's going to shut down from the outside in. Okay, it'll try and preserve the core. But then, I don't know, about after 30 minutes or so, you're pretty much okay. That's why when we did survival training out in San Diego and went in the water, they put us in a wetsuit. They if you're getting Alaska, you have to do it in a garage situation. All right. So how much for a given amount of heat energy is added? The property is called starting. And again, we looked at the. There is a table on page. Actually, it's not 29 anymore. It's in page. I think it's in chapter 5. I got to change that. It's in chapter 5, and we already saw it on the table. I'll stop. All right. The next thing we're going to look at is sounding, and then we're going to look at the energy heat balance. So there's energy heat balance. So if you would, between now and Wednesday, go ahead and make sure you have read up on chapters 5 and 7, I believe it is, in your handbook, and have your chapter 2 notes worked out, or at least a good start on, and then cover your chapter module 1 notes and do tonight. If you haven't done them, please do them up. And I'm done. Any questions, comments? Go by the way. Right? Don't get too warm going out of here, right? Well, there you go.
Switch days.
All right.